Okay, it's a little past 1 o'clock on the Eastern time. My name is David Frere. I'm stepping in for Jim Jackson, who's in Charlottesville at our yearly NSF program review. Um, so welcome to the GBO Community Zoom. Just a little bit of news. We have our public Jansky lecture is tonight. Ken Kellerman will be delivering that lecture. And we have a public star party this Saturday. It'll be cold, but it should be clear. So come on out if you're local for that, or you can come if you're far away too. And as just a general reminder, you can always check our social media for upcoming GBO events. In terms of the observatory itself, I mean, it's been nice cold weather. We've been getting a lot of high frequency time recently, which has been exciting. So I'm going to hand it over to Jay Lockman, who will be introducing our speaker. So.
Thanks, Dave. This week's presentation is by Tom Donlon from the University of Alabama, Huntsville. He'll speak on pulsars as accelerometers, exploring binary pulsar systems and the Milky Way. Let me remind everyone that this is being recorded for later viewing on the GBO website. And if you have questions, there'll be a chance to submit them at the end through the Q&A box on the bottom of your screen. Okay, take it away, Tom.
Great, thank you. Let me just share my screen here. Perfect, all right. Thank you for the great introductions. We can hop right into the content. So I'm going to talk just a little bit as a primer on what we actually mean by acceleration and how we measure these things. So pulsars, which are typically neutron stars that have very strong magnetic fields, and as they spin, that causes them to shoot out large beams of charged particles, and we see those as flashes of light on Earth, and they come around very, very on time. They're very stable because there's not really much that can impact the rotation rates of pulsars. They just kind of emit things and spin freely. And that lets them, they're very precise astronomical clocks that lets them be used for some really cool physics. Most recently, you might have heard some things about the stochastic gravitational wave background that nanograv, as well as other pulsar timing arrays have made attempts to measure. And so I'm going to be talking about something kind of related but different. We're going to be using that pulsar timing data to get accelerations. The reason that we can get accelerations is basically from a Doppler shift. So a Doppler shift is like if you have a car that drives by you on the road, its sound kind of, it goes up in pitch and then down in pitch as it passes you, right? It goes as the car drives by you. And the reason for that is because sound, or any wave, is modulated by the speed that something is traveling towards you, away from you. It compresses the sound waves in one direction. And that's the same for pulsars. Pulsars have this very periodic light beam that comes around on time. And if the pulsar is traveling away from you or towards you, that's also going to then be Doppler shifted. If you have an acceleration, which is a change in velocity, then how much that is modulated will change over time. And that looks like a change in frequency of the pulsar. It looks like the pulsar rotation is speeding up or slowing down. And so that lets us actually measure the change in velocity, which is an acceleration. And you can get these very, very precisely. It turns out that the accelerations that we're measuring, something like if a star is orbiting around the center of the galaxy, you have an acceleration of something like a few millimeters per second per year, which is an insanely small value. And because of how precise pulsars are, we can actually measure something that small. So you can see over on the right, you have these sorts of pulsar timing residuals. You have something messy like what's up in the top. And so the people at Nanograv and these other pulsar timing arrays have worked very hard to take out all of these effects from the Earth's motion around the sun's motion in the galaxy, the pulsar's motion on the sky, all these other things, in order to get these very clean residuals that we can use to get accelerations for pulsars. And we've been able to do some really cool things with pulsar timing already. We have about 25 to 50 of these pulsars that we can use for accelerations. And that is now letting us do some cool things like constrain the density of dark matter near the sun. So these accelerations tell us how much of the gravity near the sun is caused by dark matter pulling on these pulsars. And we can measure that, and we're now getting things that are consistent with other values that people have obtained using the motions of stars in the galaxy. And that's shown on the left there. On the right, what I'm showing is that there's a weird feature in the acceleration data for the pulsars, which is that there's a stronger acceleration above the plane of the Milky Way than there is below the plane of the Milky Way. So you think of the sun is right in the Milky Way disk. And if you look up, the acceleration towards the disk is stronger than if you look down and see that acceleration. And that is probably due to interactions with other dwarf galaxies that are orbiting the Milky Way. I'll talk a little bit more about that in a couple of slides. So as we were going through and I was compiling all of the pulsar accelerations, we kept an eye out to see if there were any accelerations that were statistically inconsistent with just being due to the acceleration of our galaxy. And it turns out that, yes, there is one. And that pulsar is J2043 plus 1711. I'll probably just call it J2043. And it is a binary pulsar. So it's a pulsar that's orbiting a white dwarf companion. And what we observe is that it has an acceleration of nearly 4 millimeters per second per year, which is an insanely small number when we're going about our Earth lives. But it's very well known because of how precise the data is for this pulsar, and it's over 4 sigma away from what we would expect from the gravitational acceleration of our galaxy. So on the right, you have all these blue bars, and that's these pulsars that we're observing. They should all be close to that linear fit line there, that gray dashed line. And you see that the red triangle, which is J2043, is super far off from that, and the error bars aren't very large. So that tells us that something interesting is happening with this pulsar, and we want to discover what that is. And so I kind of was thinking when I was coming up with some of this work, it's kind of, we're doing detective work, right? We see this strange thing and we have to go through and identify all the weird stuff that could possibly be causing this anomalous acceleration. So I kind of imagined it like a space detective novel or something silly like that. And it's a fun way to think about some of the work that we do. And so the first option that we're going to examine here is, could J2043 be a spider pulsar? So spider pulsars are a class of object where these pulsars are emitting all of this energy, these charged particles. And if it has a companion object, so something that's orbiting along with the pulsar, then that companion can be blown away by these jets if they're if they're aligned in the right way, right? So you see in that picture that there's a large star that's orbiting the pulsar, and the pulsar's beams are hitting the orbiting companion, and that's causing the companion to shed some of this matter. You can see that there's like some cloud of dust that's following that object. And what ends up happening there is, because the object is losing mass from the jets of the pulsar, you end up changing the orbit over time. And that looks like an acceleration. It isn't really an acceleration in terms of the pulsar isn't actually speeding up along our line of sight, but it looks like an acceleration in the data. So I took a look at a bunch of other pulsars that we know for sure are spiders. In this case, it's called a redback, is this particular type of spider. There's also like black widows and a couple, I think there's also huntsmen. So there's this fun naming convention that people are using for this sort of thing. But in this case, it's a redback. It's where you're irradiating a like main sequence star that is losing a lot of mass. And so these known spiders on the right, they have these p dot over p. That's basically an acceleration. It's just divided by the speed of light to get the right units. you can see that you have something like 10 to the minus 16, 10 to the minus 14. Yeah, that's about the order of things that you get. For J2043, you get an acceleration that corresponds to something like 10 to the negative 19. So it's like 1,000 times smaller than what you would get from these redback pulsars. So it turns out that no, it's just not consistent with being a redback. If it was, the acceleration would be enormous, something way, way larger than what could ever be caused by what we see. Additionally, these redback companions are really bright. They just turn out that they get really hot when you do this irradiation thing to them. So we should see it. If the system was a redback, we should be able to see that bright companion, and we don't. So that's another good indication that it's not actually a redback pulsar. The next thing that we're going to check is if maybe we're just wrong about the Milky Way's acceleration. Maybe there's something going on that causes an acceleration like this just locally. And this isn't a crazy idea because in the last 10 years or so, people have realized that there's a lot of things going on in the Milky Way's disk. And really, it's because of impacts from orbiting satellites. So, for example, there's something called the Sagittarius Dwarf Galaxy, and it is actually moving. It's a dwarf galaxy, like a small Milky Way that's moving through the Milky Way disk right now. It's on the far side of the galaxy, so not near the sun, but it is hitting the disk, and it leaves this long trail of stars. I don't know if you can see my cursor, but I'm highlighting this stream of stars on the right here. That's the Sagittarius stream, and it is caused by the Milky Way's gravity stretching out and stripping stars from this dwarf galaxy. And as it impacts the disk, you get these waves and wiggles, and it's like if you throw a stone into a pond, the pond ripples outwards, right? And the same thing is happening here. We hit the Milky Way disk with a dwarf galaxy, and it causes these waves and ripples. And you can get information about these waves and ripples. That's part of why we saw that asymmetry in the accelerations in the pulsars. And it causes the accelerations to have like local structure just on scales across where the pulsars are compared to the sun. So on the left, I have a map. It's like if you're looking down on the disk, there's a map of what the acceleration is that isn't just the normal amount we'd expect from the galaxy. It's the extra stuff that comes from these sorts of waves and wiggles. And there's a couple of different simulations to show the effects of different dwarf galaxies that we know exist. And you see that, yes, there are local things that could cause pretty decent accelerations that you'd observe that would be different from what we would expect that are caused by this effect. However, they're just not big enough. The acceleration that we see from J2043 is about 4 millimeters per second per year. It's really hard to get this to make acceleration more than about 1 millimeter per second per year. And usually it's much, much less than that. So we say it's possible, it's really unlikely. What's more likely is that this is doing a little bit to this pulsar, and there's something else going on as well. The other indication is that you would see this in every pulsar in the data set, and we don't. We really see that the rest of the pulsars are more or less consistent with the gravitational acceleration that we expect to see on these large scales. So that's a good indicator that we're not seeing this in J2043. So we started digging a little bit deeper. The next idea that we had is what I call the Flyby hypothesis. There is, if you look in the Gaia data, Gaia is a space satellite that has observed photometry for billions of stars. There is a star that's very close to J2043 plus 1711 on the sky. And J2043's known companion is a white dwarf, so it won't show up here. It's too dim. What we see is a bright main sequence star, something close to like what the sun is. And it's really close on the sky. It's just a couple arc seconds away. And we know what its mass is, we know what its temperature is, these things, and we know what its proper motion is. We know where it's traveling on the sky, and that's drawn as an arrow in that image on the left there. You can see that the two objects are not moving together, so they're probably not orbiting each other. If they were part of the same system, they should be moving in the same direction on the sky, but they aren't. That doesn't mean that they aren't near each other. It just means that they are not bound. It means that it would just be a stellar flyby, like a star that just randomly passes close to the pulsar, flies away, and right now we happen to catch it when it's causing a large acceleration. And so, because we know what its mass is and how far away it must be, we can figure out the distance between the two objects in order to, if it did explain the acceleration that we observe, how far away they need to be. And it ends up being that they would be about 7,000, 8,000 AU away. And just for comparison, the Oort cloud of the Milky Way is like what we call the boundary of the not the Milky Way, sorry, the Oort cloud of the solar system, what we consider like the boundary of our solar system, is like 10,000 to 100,000 AU. So that's very close. This would be like if a star were to pass within like just a couple Neptune orbits away from the sun. That's how close this flyby would need to be. And it's not crazy, you know, this is a thing that statistically it's unlikely, but not insane that we would just happen to see this. It's like a 1 in like 1,500 chance. So not outrageously crazy, but very rare and unexpected for sure. The other thing that we said possibly could happen would be if the pulsar and its white dwarf companion had a circumbinary thing. So there's some planet or star that's orbiting around the other two at a much larger orbit. And because that orbit is so large, we don't see it change over time. It would be like a 500,000 year long orbit or something like that. But there's this really cool way to figure out if these things are there or not. It was by Megan Jones and David Kaplan et al. A couple of years ago, who noticed that the acceleration that you get if you have this circumbinary thing is just a sine curve. It's like a radial velocity curve that you get from a planet or something. As it orbits in a circle, it pulls it away from you and then towards you, and that oscillates back and forth. If you take derivatives of that, you'll get sine curves with a specific change in the sign of you'll get like the sign like plus or minus, not sine curve, of the derivative. So it should, and that tells you where you are in the orbit. It also tells you that it is actually changing the acceleration in a way that is consistent with a circumbinary object and isn't just some random fluctuation that you happen to see in the data. And it actually turns out that what we see for this pulsar is consistent with that. And you get something that has about I think 20,000 year long orbit. And it would have a mass that is like half to like 0.7 solar masses or something. So a star. And then you also get some orbital configuration stuff out of that. So to wrap up, millisecond pulsars are really cool. They can be used as accelerometers, among other things, and that's valuable for people who do galactic dynamics stuff like me. And it turns out that some of these things should have statistically significant peculiar accelerations, and we observe that for at least one pulsar. There's a number of things that can cause that, and we go through them and check to see if it is a possibility for this particular object. One is like if it's a spider pulsar, and that ends up being no. Is it just some weird dynamical feature in the Milky Way? Probably not. But there is some evidence that what we have here is actually some either a circumbinary companion that was previously unknown, or that there's some stellar flyby, or some combination of the two, or something like that. So that's all that I have. Happy to take whatever questions. Thank you.
Thanks very much, Tom. Fascinating talk. Please submit your questions in the Q&A box at the bottom of the screen. And I'm going to start by one of mine. How far away is this pulsar?
It's like 1.7 kiloparsecs.
Okay, well, you said it was a couple of arc seconds away from the projected away from that star. That's really quite a large distance then, isn't it, at a couple of kiloparsecs?
Yeah, so it's not super big. At a couple of kiloparsecs, we have it split out here, and you can see the trig that we did. So the on-sky projection is S then, and S only ends up being, I think, 5 or 6,000 AU. I'd have to look at the actual number. So it just kind of ends up working out that they are the right distance away to actually be consistent with it. And yeah, so it is an arc second at 1.7 kiloparsec sounds like a lot, but it ends up being like 6,000 AU, which isn't a ton. It's definitely not outrageous that these things would have a large acceleration on the other.
Mhm. Okay, and we have another question. Are you seeing any trends in the dispersion measure?
Oh yeah, great question. No. So nanograv, which this is a nanograv pulsar, is very, very careful to consider whether there's changes in dispersion um, measure, or also if there is like strong red noise, which is probably related to dispersion measure usually. And they don't see any of that in this pulsar. They said there was no statistically significant red noise, no changes in dispersion that they could see. So that is almost certainly not what's causing this. Yes, great question.
Okay, there's another one. In the slide of the detection, I guess, which shows the acceleration, um, there's another pulsar at about 7.6 kiloparsecs that has very small error bars, also inconsistent with the linear fit. Um, and would you comment on that other pulsar?
Yeah, yes, that is, shoot, I can't remember which one that is off the top of my head. Um, it is probably like 3 sigma, maybe just short of 3 sigma. Um, yeah, I can't remember which one it is. There's a couple that have um, that sort of significance. There's also like one at like 9 kiloparsecs that has, uh, it's not quite there. It's like 1.5 sigma or something. Uh, and so, yeah, there are definitely, each pulsar is unique. There's interesting things going on. We just haven't gone around to looking at that very carefully because it wasn't as significant as this, as J2043. Um, but
There's
yeah,
yeah,
if you're interested, feel free to shoot me an email. I can tell you which one that is. I don't remember off the top of my head, but I must be able to figure that out very quickly.
but even if they're at similar galactocentric distances, doesn't mean they're anywhere near each other.
No, yeah, that's right. Yeah, they can be 4 kiloparsecs apart,
Yeah.
but still have the same galactic radius on this plot.
Okay, we have another question. As with the Sagittarius interaction, if it were to bring a clump or higher density dark matter blob, could a pulsar acceleration nearby be able to detect it?
Yeah, yeah, absolutely. That's actually something that I've been very interested in and have started to kind of work on a little bit. It's still very early days, but yeah, so you do expect in our modern theories of dark matter, you do expect that the Milky Way has like a clumpy dark matter halo. So all the dark matter that's surrounding the Milky Way, it shouldn't just be completely smooth for most of our theories of dark matter. It should have like structure to it. And that structure will cause accelerations to be stronger in one direction than the other. And that changes as a function of where you are in space. And yes, you could, in theory, observe that for pulsars. So it is possible, um, very unlikely in this case for J2043, but possible that what you're seeing is some local dark matter structure that's causing a large acceleration only near this pulsar and not near others. It's hard to do. It's hard to make that dense of dark matter substructure on scales like that. But what you do expect is that over a few kiloparsecs, you should get clumps of dark matter that are something like uh, a million, 10 million solar masses, and those are just flying through the galaxy all the time. And if one of those were to just pass near the sun, you should see that in the accelerations of the pulsars. And that is something that we're working on, being able to see if we can test for that sort of thing. So it's a really cool idea. Definitely want to explore that more.
How about giant molecular clouds?
Yeah, those are the same deal. They can cause these sorts of accelerations also. The good thing about giant molecular clouds, though, is that we know where they are, right? For all the giant molecular clouds within I forget how far, but like 4 kiloparsecs from the sun or something, we should know where they basically all are and how massive they are. And so we can look and see, is there a giant molecular cloud there? Yes? Okay, great. Then there should be this much acceleration. We can check for that. There is not a giant molecular cloud that's near J2043 that would be causing this. So we did check for that as well. But in principle, yes, you can do the same thing with giant molecular clouds. And so it's good to kind of, the lucky thing is that you can get rid of that because we have a map of where they are.
Could you go back to the slide with the accelerations on that shows the deviation? Yes. Um, what does the dashed line represent?
This is okay. This is, I was worried about putting this on because I figured someone might ask this question. Not that it's a problem, but it's a little bit not related to this. Uh, we noticed that there's this like maybe this radial trend in the accelerations of the pulsars that we observe. And so what you get is that there's like a positive the pulsars that are closer to the center of the galaxy, they have smaller r, are being accelerated away from us more than we would have expected. And the pulsars at larger galactocentric radii, so over at a like 9, are being accelerated less than we would have expected. And if we were correct about the galactic acceleration, they should be scattered around 0, just evenly and flat, but they aren't. There's like this linear term to it. That cannot be caused by getting the mass of the galaxy wrong. It cannot be caused by getting the slope of the rotation curve wrong. What can cause it is, the only thing I've found so far that can cause it is if the sun is feeling an acceleration with respect to the center of the galaxy that isn't accounted for. You could have something like Planet 9 can do that. And interestingly enough, Planet 9 is where the current constraints on what Planet 9 would be and where it is. It's in the right direction to cause this sort of acceleration. So I wrote a little bit about that in a 2024 paper that came out earlier this year on like using these to make a map of the acceleration of the Milky Way. So I talk about it a little bit there. It's probably the case that there's other things that can cause this. You know, it's possible that as we get better pulsar data, it might also go away. It might just be that there's something weird about the measurements that makes it look like this, and it's not really that significant. But it's an interesting thing, and the only thing that I've been able to show that actually does lead to this sort of effect is like the sun has a peculiar acceleration for some reason that we're not accounting for. Sorry, I know that was a long-winded answer, but it's, yeah.
We have time for one more quick question. Do we know of any pulsars in Andromeda yet? The Andromeda Galaxy.
Ooh, I don't know.
I think the answer is no, unfortunately.
I think so too,
Yeah.
because they are pretty faint. They're hard to spot. And it's just that the beam of light that you see from them falls off so much as they get farther away. I don't think that there is, yeah.
Yeah. Well, that ends all the time we have today. Thanks very much, Tom. I feel in a way that we're witnessing the start of another whole era in galactic astronomy. So thank you very much. And as I mentioned earlier, this has been recorded, and so you'll be able to see this on the GBO website in a day or two. Please join us for our next in this series of webinars on Wednesday, December 18th. Gabby Wenzel of the Massachusetts Institute of Technology is talking about detections of some complex interstellar organic molecules in TMC1. Please join us then. Thank you and goodbye.